Hello and welcome. If you have been curious about generative AI but were not sure where to begin, then this series is for you. Over the last few years, we have all experienced the power of generative AI through everyday applications that generate content, answer questions, analyze information, and assist us in countless tasks. But there is a big difference between using an AI powered application and building one. Production AI systems require much more than a foundation model. They need careful planning and implementation of orchestration, memory, retrieval from knowledge sources, tools for taking actions, security guardrails, evaluation, and operational reliability. This course is about that journey. In the first two episodes, we will begin by learning the fundamentals and understanding how these models actually work. In subsequent sessions, we will gradually build up to designing, developing, and deploying enterprise grade generative AI applications. Throughout the series, we will combine theory and practical demonstrations using open source frameworks and cloud services for building real applications. You do not need any prior AI/ML experience to learn in this series. My goal is to explain the important concepts intuitively without oversimplifying them. The series is intended for a broad technical audience, whether you're an architect designing solutions, an application engineer, a technical leader who's evaluating AI initiatives, a product manager, or even a domain expert who works closely with engineering team, you will find something valuable here. My goal is that by end of the series, you should be able to look at an enterprise-grade generative AI solution and immediately recognize the major building blocks and how they fit together. More importantly, you will develop the ability to reason about architectural trade-offs. Every design involves balancing accuracy, latency, cost, scalability, security, and governance. Understanding these trade offs can be far more valuable than memorizing any particular framework. This knowledge will also make you comfortable in participating in technical design discussions. Even if you're not writing the code, you should be able to ask the right questions, understand an architectural diagram, and contribute confidently to any design decisions. Throughout the course, we will explore both open source and commercial tools in the demos. Although we can only explore a limited number of tools, you will gain familiarity with the key concepts and popular tools that are available for various technical components. This will get you started with your own exploration for the right tools for your use case. To begin understanding generative AI, a good way is to compare it with traditional programming technique that have dominated the software development for decades, and we are all very familiar with them. In traditional programming, a development team explicitly writes the business rules. During development, the developer translates these business requirements into the code. And when software is deployed in production, new data flows through these predefined rules to produce the output. Today, with AI powered coding assistants and vibe coding, writing code itself has become much easier. However, what hasn't changed is that we still need to understand the business problem so that we can translate into precise rules and algorithms. And this translation step is often the hardest part as the complexity of use case increases. Some problems can have clear rules, for example, calculating taxes or determining shipping costs. These are deterministic problems. That means for a given input, we can create rules to always produce the same output. But many real world business problems do not work this way. For example, consider reviewing a legal contract, or answering questions over thousands of documents, or maybe drafting a response for a customer complaint. For each of these use cases, even if a team of experienced developers were to write explicit rules, they will quickly discover that number of rules becomes enormous and difficult to maintain and often impossible to enumerate completely. And this is exactly where machine learning and especially generative AI becomes a natural fit. Instead of manually writing every rule, we provide example data during training, and the model learns statistical patterns from the data. When this model is deployed in production for inference, it applies the learned patterns to new inputs and predicts the most likely output. And this brings us to another important difference. While traditional software is deterministic, which means same input will always produce the same output, machine learning models are probabilistic. Machine learning models estimate probabilities of many possible outputs based on what they have learned during training, and then pick one of these most likely answers. That is why the same prompt in ChatGPT can produce a slightly different response every time. The non deterministic nature of generative AI fundamentally changes how we test and monitor these applications. Because we do not have a fixed answer, rather than checking whether output is simply right or wrong, we evaluate if it satisfies the user's intent while remaining accurate, relevant, safe, and helpful. The evaluation happens throughout the life cycle, from development, testing, to continuous monitoring in production, creating a feedback loop that helps maintain and improve system quality. And this focus on quality based assessment and continuous evaluation is a key difference in the mindset when building a generative AI solution. Another way to understand generative AI is to see how it fits within the broader field of machine learning. Let us look at the evolution of AI over the years. The first major wave of modern AI was machine learning, where the primary goal was prediction. We collected structured tabular data such as house features or customer attributes and trained models to predict outcomes such as house prices or customer churn. During this phase, developers created mathematical models by explicitly choosing the mathematical equations that can learn patterns from historical data for a real world problem. And in this era of machine learning, inputs were structured and outputs were simple, straightforward predictions such as class labels, a probability, or a numerical value. However, as data became richer, we entered the era of deep learning, where instead of relying on manually engineered structured data, the model learned directly from complex unstructured data such as images, speech, and large amount of text. This enabled AI systems to tackle problems that were previously difficult to solve, which mainly include recognition problems such as natural language understanding and sentiment analysis, image recognition, speech recognition, etc. While these models were still making predictions, we could now process far more complex data as input. And the next wave is generative AI, where rather than being limited to recognizing or classifying information, as with previous generation models, the models can now generate entirely new content. I'm sure you have explored creating images, videos, or summarizing your documents or writing code using foundation models. The output is no longer just a label or a number, it can be rich human like text, images, videos, or audio. One important thing to notice here is that generative AI is a subset of deep learning. It did not replace deep learning, it is built on top of it. And this is an important connection because when we start looking at generative AI architectures, we will first learn about neural network and gradually make our way towards transformer architecture that powers today's large language models. Let us review the key features of generative AI technology. The first characteristic is that it can create new content. Second important idea is a foundation model in generative AI. Traditionally, we used to build separate AI models for separate tasks, such as classification, spam detection, translation, etc. Today, a single foundation model can perform many different tasks by simply changing the input prompt that you provide. Another major shift is that language has become the interface. Instead of defining forms with fields and graphical interface or writing complex queries, we can simply describe what we want using natural language and the model understands it. And as we discussed, these systems produce probabilistic outputs. which means that there are many possible outputs for the same input prompt. And many foundation models are multimodal. While language models are the most familiar examples, many modern foundation models understand and generate multiple types of information, which includes text, images, audio, and video. You can provide a text input and generate an image, audio, or video, and vice versa. Now, let us look at some popular model architectures that generative AI is built on. Each is defined for a different type of task. Transformers architecture powers today's language models such as GPT, Claude, Gemini, Llama, etc. These models excel at understanding and generating the text. Diffusion models are primarily used for image generation. They are trained to start with random noise image, as you can see on the left, and progressively remove the noise, transforming the image into a realistic image that matches user's prompt. Another emerging generative AI architecture is flow matching, which is gaining traction for video generation, 3D content, and scientific simulations. Like diffusion models, these models also generate content from random noise. However, instead of gradually defining the output over many iterations, they learn a more direct path from noise to the final result. This technique has a potential to make generation faster and more scalable, making flow matching an exciting area of ongoing research. And these architectures are not competitors to each other. Modern multimodal foundation models often combine multiple architectures from behind a single API, allowing them to understand text, images, audio, and generate different types of content. In this course, we will focus on transformers models only because they power the foundation models that most enterprises use today. In the next episode, we will take an intuitive and non mathematical look inside Transformers architecture to understand how it works. As an application engineer, you will typically never train or modify a foundation model unless you are customizing it with your own data. However, understanding how Transformers architecture works at a high level will help you better interpret their behavior, capabilities, and limitations when you build your AI applications using them.